proportional to acceleration. He is almost there. He's just missing a proportionality constant. Right? He's almost there. And he came up with another very important concept, that is the centripetal force. Like I said, we need to remove any misconception coming from undergraduate study dynamics, and one of these is the centrifugal force, right? There's nothing called centrifugal force, just leave that from your mind. If you remember, the centrifugal force was if you have a turning object, there is a centrifugal force out from the center. There's nothing such a thing, okay? There's no such a thing. The thing is, if you have an object and you want this object to turn, of course I don't care at all about the object turning around itself. I'm talking and I'm concerned with the velocity vector of the object. I want to turn the velocity vector of the object, okay? If you want to turn the velocity vector of any object, you need to apply a force perpendicular to that velocity to the center. This force is called centripetal force, and is found by Huygens. Okay? We found two very fundamental concepts in the history of dynamics. Force is proportional to acceleration, is almost there, and the concept of centripetal force. Then the greatest in dynamics, Newton came, like I said, December 1642. And since the time of Newton, dynamics can be classified in two main branches. Newtonian mechanics, which we studied mostly in our undergraduate version. Sometimes we call it vectorial, we're going to see why. And the analytical or variational mechanics, it's typically studied in graduate school, which is the main topic of this course. Newtonian mechanics is mainly concerned with particle motion in Euclidean space. What do you mean by particle motion, or what do you mean by Euclidean space? Particle is an object whose motion is not affected by its shape. It's not affected by the shape. It's not like this disk, where during its motion it will turn around itself, and the shape will matter because the motion will be affected because this shape has three axes, has a moment of inertia about each axis, and probably the rotation will be about the axis of less moment of inertia. The easiest rotation will be about the axis of less moment of inertia. No, we're not talking about these bulky objects whose motion is affected by the shape, by their shape. Just point masses, okay? Point masses moving in Euclidean spaces. Euclidean space is a flat space, like this x, y, z, okay? It's not a curvy space, for example. So this is Newtonian mechanics. Later on, we can collect all these point masses and gather them in a body like this, right? So where these particles, we will assume that they are just rigidly connected to each other. We're going to talk about this and call it as a rigid body. But still, Newtonian mechanics per se is just concerned with each particle. You're going to apply it for infinite number of particles constituting this body. That's perfectly fine. Okay. Newton laid down the foundation, or he postulated something called the principle of determinism. What's this? So Newton assumed that the current position and velocity of each object should completely determine its future position and velocity. So if you know the current velocity and position, you should be able to determine the next velocity and position. Of course, if you know the forces, but in the absence of forces, these should suffice. These two pieces of information should suffice. Which, if you want to express this mathematically, it's stated as follows. The acceleration of the particle is just function of its position, velocity, and perhaps time. Because I have now this, whatever, maybe nonlinear differential equation, time varying, I don't care. This differential equation, if you give me the initial position and velocity, I can theoretically integrate it and get the next position and velocity. So this is his principle of determinism. And now you can see immediately how you can benefit from the principles by Galileo. Actually, Newton benefited much from others, Galileo and Kepler, and he stated that in several times. One of the most expressive statements that he stated is that if I've seen further, it is by standing on the shoulders of giants. Actually, he accepted Kepler's laws, while Galileo's didn't. He didn't accept Kepler's laws, and this is why when Newton accepted Kepler's law, he developed his gravitational law based on Kepler's law. If you look at this principle of determinacy, that the acceleration of the particle should be function of its position, velocity, and perhaps time. And we're trying to develop a universal law, right, that governs the dynamics. So you can see now, okay, you, Newton, if you want to develop a universal law, then it should be applicable at all times the exact same way, which means that this dependence on time should be dropped down, right? It shouldn't be function of time. That's one thing. Next, if you apply this equation to inertial systems, it should be in the exact same way. It cannot depend on the absolute position and absolute velocity, but the relative position and relative velocity with respect to your frame. Because these quantities will be different from frame to another. The absolute position is different from a frame to another. And the absolute velocity is different from a frame to another. But the relative positions and the relative velocities, they will be exactly the same in different frames. So if you apply Galileo's principles of inertial systems, you immediately will modify this principle to the following: that the acceleration is not function of time anymore, and if it's a function of anything, it will be function of only relative position and relative velocity. And from here, you can actually prove that the acceleration of a single particle in the absence of forces is simply zero, Newton's first law. Like I said, he accepted Kepler's principle about the interactions between bodies, and this was the basis of his gravitational law. And among all these were the best or the most impactful outcomes. His laws of motion, which we study in high school and of course in undergraduate dynamics. The three laws of motion that we know. And the most famous is the second one, which is forces, mass times acceleration. Surprisingly, he called them axioms. You know what axiom means? Axiom means is something that is accepted, generally accepted, without proof. Without proof. It's an assumption. So it is very surprising that Newton's law, F equals ma, that governs the flight of airplanes, space shuttles, submarines, and how the leaf, the tree leaf falls. This is just an assumption. It's not proof. It's very, very interesting, and it's scary a little bit. And actually, this is why it's not right all of the time. In the very, very large scales, Newtonian mechanics fails. So Newtonian mechanics cannot predict the weird motion of Mercury. And this is where relativistic mechanics kicks in. And in the very, very small scales, Newtonian mechanics again fails, and this is where quantum mechanics kicks in. So F equals ma is not right all of the time. Surprisingly, it is very sufficient and correct in our length scale that we live in. Okay? But I have to admire his boldness. So this is the law that we all know about. Force is the rate of change of linear momentum, and if the mass is constant, you get F equals ma. I have to admire his boldness, and I've never seen such boldness in my life, because you can say, let us assume that force is proportional to acceleration. That's perfectly fine. At least people nowadays will agree with you. I don't know in the 17th century what they did with him, but let us assume that force is proportional to acceleration. It makes perfect sense, because the more you push, the more acceleration you get, right? But let us assume that force exactly equals mass times acceleration. This is very bold. Let us assume equality. This is very bold, and you can never see it. I mean, if you take heat transfer, right? We all know that the temperature change is proportional to the heat flux. But there is a proportionality constant, we don't know it, and we have to go to the lab to get it, right? In fluid mechanics, we have the viscosity. In structural dynamics, we have the Poisson ratio and the modulus of elasticity and rigidity modulus, whatever. In every single discipline, you have your proportionality constants. You cannot assume equality. But he assumed equality, and guess what? It's damn right. So it was very surprising. And we, like I said, the beauty of it is that it's damn useful. We use it every single day, right? We use it in designing this building, designing airplanes, whatever. Okay, so this is Newtonian mechanics. It's nothing but Newton. He established Newtonian mechanics and he finished it. So the whole branch is about just if equals ma, how it evolved. There is one more extension, we're gonna talk about it later, but it's a minor one. You can immediately get it from Newton's equation. Whereas the other branch is full of extensions. It's a very rich history. The other branch, to my knowledge, started with Leibniz. And you can see from the dates that he was contemporary to Newton. My guess, I don't know, he was jealous of Newton. Because if you see here, what is the most fundamental quantity of Newton? Well, it's the linear momentum, mv. He said, you know, no, actually, the fundamental quantity is mv squared. It's not mv, but mv squared. mv squared, he called it vis viva, which means living force. In nowadays terms, it's the kinetic energy, right? It's twice the kinetic energy. Okay? That is okay, Leibniz.